What's up guys, welcome back to Dynamic Programming for Beginners. This is part 14. We continue to massage the coin change problem. We're going to review another variation of this problem. But before we get started, here is a quick off topic, sort of like a self-promotion. So, every time I want to start a project, the very first thing that I do is I try to find a cool and unique domain name. I'm sure many of you were in a situation like that. So you come up with a ton of different words, then you go to a domain name registrar, and then what's happening is that every single domain name is already taken by someone. And that just sucks. First of all, it's a huge demotivator because you don't want to start a nameless project. And then the second thing is that it's just not fair. There are so many cool domain names and they're just sitting there without anyone using them. And in the majority of cases, someone is simply reselling all of these domain names for an enormous amount of money. So, out of this frustration, I decided to create a website that has just one goal: to generate a domain name. And what's most importantly, it generates .com domain names that are always available, guaranteed. How does it work? Well, it uses an artificial intelligence model that was trained to generate domain names that have never been used before. The website URL is domainsfortherestofus.com. Check it out, it's super fun. Every time you refresh the page, it generates a new domain name for you and gives you an option to buy it via GoDaddy, Namecheap, and some other registrars. I launched it like a week ago and it actually went somewhat viral. I had more than 10,000 unique visitors within a day, which was super cool. So, if you're in the market for a unique domain name, give it a try. Once again, the website URL is domainsfortherestofus.com. Now, back to the course. So, in the previous lecture, we reviewed the coin change problem, different variations of the coin change problem. So the very first one was we had to find the total number of ways to make a change of size n. Then we added a constraint. We said that we want to use exactly 9 coins. Then we changed the constraint and we said we want to use no more than 9 coins, right? Or T coins as a general sort of like way of saying it. And today we're going to say that we want to make a change of size n by using an even number of coins, exactly even number of coins. So I'm going to say here by using an even number of coins. So how are we going to solve this problem? Well, the very first thing, as usual, we want to define the objective function. Let's do it. So we have f of what? So we have 2 variables here. Well, we definitely have n, right? So we can say f of I, which means I'm not going to use n here because n, I'm using I and not n because n is where the answer is, right? And then we also have a constraint here because we are modeling the problem. So we want to, each constraint we want to fit into our function. So f of I, and then the second constraint is that we have to use an even number of coins. So let's say that we'll have a parameter, let's say x, and then x will have 2 values, 1 for even numbers and 0 for odd numbers. So let's say when x equals to 1, this means even, and then when x equals to 0, this means odd numbers. Okay, great. Now let's identify base cases. This is the second step in the framework. So let's try to solve the problem for f 0, 0, meaning that we want to find the total number of ways to make a change of size 0 by using odd number of coins. We can do it, so there are 0. The answer is 0. There are 0 ways to do that. Now, f of 0, 1. How many ways to make a change of size 0 by using an even number of coins? There is one way, we're just returning an empty coin, right? Okay, let's take a look at, let's say, f of 1 0, so forth. How many ways to make a change of size 1 by using an odd number of coins? There is just one way, because we can take 1 cent. These are our denominations, right? 1, 3, 5, and 10. So if we were to return the amount of 1, we can use 1 cent, and this is an odd number of coins. F of 1, 1. So to return a change of size 1 by using an even number of coins, we can do it 0. Okay, let's review a few more cases. So let's say f of 2, 0. So how many ways to make a change of size 2 by using an odd number of coins? 0 ways, right? Because we don't have 2 cents denomination here. What about f of 2 with even number of coins? So we can just do 1 cent and then 1 cent more, 1 more cent. So there is one way, 2 ones, 1 and 1. So we are using 2 coins here, and this is an even number. Let's take a look at f of 3. How many ways to make a change of size 3 by using an odd number of coins? So the first way is we could just do 1, 1, 1, right? 3 ones. And then the second way, we could just return 3 cents. So there are 2 ways. Now, what about f of 3 even number of coins? Can we do that? I don't believe so. So we can't use ones because we'll end up with... Oh, we actually can, right? We can just do... No, we can't. We can't. 0. 0. Okay, so these are the base cases, right? A few base cases here. Now, let's try to come up with a transition function. I'm going to clean this part and then try to hit the pause button and maybe try to come up with a transition function by yourself first. Because in the previous lecture we reviewed by using exactly 9 coins, then we reviewed by using no more than 9 coins, and today we're doing an even number of coins, right? It's just a different variation. So maybe you will be able to find the transition function by yourself. Meanwhile, I'm going to show it to you here and explain. So we'll have to write down 2 transition functions because we have x equals to 1 and then when x equals to 0. So let's take a look. So f of I 0 equals 2. So how can we start making a change? We can start from 1, 3, 5, or 10, right? Let's start from 1. Right now we're in this state, f of I 0, and we want to transition to the next state. What is going to be the next state once we return 1 cent away? So we will be in the state when we have 1 cent less, right? So this I is the amount, just as a reminder, this is an amount. And if we return 1 cent, we'll still have to return I minus 1, right? This is the next state. Now, if I were to have some amount of coins, some number of coins in my hands, not some amount, if I were to have an odd number of coins in my hands and then I would return 1 cent, 1 coin, right? What I would end up with is I would end up with even number of coins, right? So the next state is I minus 1 and even number of coins. Now we have to, so this is for when we start making a change from 1 cent. Now we'll have to consider other denominations, and the transition function is basically, the pattern is basically the same. So we end up with I minus 3 cents, and we also end up with an even number of coins, plus f of I minus 5 plus f of I minus 10, and then even as well. What happens when we have an even number of coins? So f of I 1, it's basically the same, just the x is going to be the opposite, right? So it's going to be f of I minus 1, and then so we had even number of coins, and now the next state we have odd number of coins, and so on, plus blah blah blah. The rest is the same. I minus 3 0, I minus 5 0, plus I minus 10 0. So this is the solution to the problem. I hope now you see the pattern when we solved, like the exactly 9 coins or t coins, no more than t coins, and now even number of coins. Let's code it up and see what happens. All right, so here is the problem: coin change. Given an unlimited supply of coins of given denominations, find the total number of ways to make a change of size n by using an even number of coins. So let's recall the transition function. F of I0 equals to f of I minus 1, 1, plus f of I minus 3, 1, plus f of I minus 5, 1, plus f of I minus 10, 1. And this transition function is for denominations 1, 3, 5, and 10. And then we also have the same transition function for even coins, even number of coins. And these guys are just the opposite, right? So here is the function, coin change. I'm going to initialize an array of size, it's a two-dimensional array of size n plus 1. And now the columns, I have dp of I is an array of size 2. The reason why the size is 2 is because we'll have dp of 0. Well, that's because we have either 0 or 1 here, right? So the size of the column is 2. Okay, so now we'll return the answer. It's dp of n 1. Now we can identify base cases. So we know that dp 0, 0 equals to 0. dp 0, 1 equals to 1. We're just returning an empty coin. Now we can start our loop starting from 1 all the way up to n, and we can apply the transition function. dp of I0 equals to dp of I minus 1, 1, plus dp of I minus 3, 1, plus dp of I minus 5, 1. And the same for even number of coins, 1, 0, 0, 0. Okay, now we want to take care of corner cases. Actually, plus dp of I minus 10, 1, plus dp I minus 10, 1, 0. So we want to take care of corner cases so for this guy, we want to say if I is greater or equals to 0, then, or we can say when I minus 1 is like so, greater or equals to 0, then dp of I minus 1, 0, plus equals dp of I0, I minus 1, 1. And then the same for the opposite, 1, 0. And we can do the same for the other 3 denominations. dp of I0 plus equals dp of I minus 3, 1. dp I1 plus dp I minus 3, 0. And we can do the same for the other two. I'll just copy and paste as usual. So we have 5, I minus 5, I minus 5. And then I minus 10, I minus 10. All right. So now we've taken care of all the corner cases. Let's test if this code works. I have a test case over here. Okay, so 2 cases passed, which is good. This one is actually number 2. And the last bit here is to actually use the coins, the denominations array. So we can comment this whole thing out and we can say for each coin in the coins array, if I minus coin is less than 0, then we can continue. Otherwise, we can say dp of I 0 plus equals dp I minus coin 1, dp I 1 plus equals dp I minus coin 0. And that should do the trick. Let's see. Let's go to the test. Let's run the tests. And everything is good. So as you can see, guys, when n equals to 4 and we have denominations 1, 3, 5, and 10, the even number of ways to make a change of size 4 is 1, 1, 1, 1, all the ones. Then we can do 1, 3, and then 3 and 1. You see 1 and 3 and 3 and 1 are different ways of making a change of size 4. In the next test case, I have 6. So all the permutations of 1, 1, 1, 3, 1, 1, 1, 3, 1, all of these guys are different ways. So we end up with 8 different cases. In the next video, we'll review a coin change problem in which the order does not matter or matters, depends on how you look at it. But anyways, we'll review a coin change problem in which we have to find the distinct number of ways to make a change, and we'll review how exactly we can take care of the distinction between all of this, guys. Thank you so much, guys, and I'll see you very soon. Take care. Bye.